Hello everyone. As promised, I'm going to be doing the Chapter 2 lectures as a series of shorter lectures and breaking them up into smaller videos. And then hopefully that way that'll enhance your learning and be able to keep you focused since we're going to do a shorter period of time for each of the lectures. Rather than an hour and 15 minutes, I'll try to keep it around 15 minutes or so for each section. Okay, so this is Chapter 2 out of our book. It's Mechanical Behavior, Testing, Manufacturing Properties of Materials. Those are the basic topics in the class. Some of it's going to be repeated in more detail from previous chapters and discussions, but hopefully it'll bring it all together for you and you'll have a firm understanding of these different concepts. So you should, by the end of the lecture series, demonstrate your understanding of the effects of external forces on materials, and also understand bulk modulus as applied to a cantilever as well. So, all materials, when you design them, have external forces on them, and you need to design your devices, gadgets, buildings, whatever the case may be, to withstand those forces so it doesn't cause a catastrophic failure. So a large portion of your understanding as a designer is what are the material properties, how do we shape these materials to form our components to our devices, and how do we do that so we stay in a safe zone and our factors of safety are met. So this picture here is of a giant cantilever, and you can imagine what the forces are in the end of that cantilever, wanting to have it topple over into the pit there. So a lot of engineering work went into that to make sure that this thing does not fail. And it does not fail over time. All right, so here's some key testing concepts you're going to learn about. There's tension, right? Pulling something apart. Compression is pushing it and compressing it. There's bending kind of testing that we can do. And then the material itself has a certain hardness. And there's also fatigue and creep testing. So fatigue is, dynamic testing. You're changing the strain or the stress. You're changing the stress on a material in a periodic fashion. Usually it's a sine wave. And then you have you set a certain stress amplitude and you look at it over time and you see how many times you can cycle that vibration in your system until it fails. And creep is, for example, you make a beam and you put 1,000 pounds on the beam and see how long it takes for it to break. And that's under a static load. So by the end of this series, you'll know the definitions. You'll be able to do some simple problems and have a good idea of how material properties impact and can impact your design. Okay, so this is one of the first tables in the chapter, and it basically ranks the different parameters of materials, properties of materials in rank order. So top being, for example, in the first column, the top is the highest strength and the bottom is the lowest strength. So as you can see, glass fibers are extremely strong, while lead is not very strong. You can pull it apart. Same goes with hardness. You got diamond. We all know it's a really hard material. And lead, of course, is very soft in terms of hardness, and so is tin. And toughness, we'll learn about what toughness and how that is defined. So for ductile metals, which is most of the metals you'll be working with, the toughness has a well-defined definition. And glass, of course, is not tough. And you get the idea. So take a look at this table and make sure you learn the definitions of all of the different headers on there by the end of the chapter. So a lot of what we do in mechanical engineering is based around tension testing. Okay, tension testing is actually pulling on a material and seeing what happens. So let me get my little pen out. This is a tension tester on the left side. And what we do is we clamp using the grip a sample, right? That's this light blue dog bone looking sample piece. So you take your material, you form it into this shape, and there's certain specifications to follow to get certain shapes. And then you clamp it on both ends, and the tester will pull on that sample piece. So this is held in place at the base, okay, and then we pull up on it, which will create a force pulling up on the sample, okay, and you keep pulling, and you can imagine it's going to start to stretch, okay. And usually what they do is they'll have two indicators lightly attached to the sample, and then as this stretches, this L naught gets longer, becomes L. L naught is the original length, starting length. So then you start pulling it apart, and it starts stretching, and these little index fingers here that are connected to the sample will move apart as well. And as they move apart, you know, as this moves up, L gets bigger, okay, and we track how much we stretch it by as a function of the force that we put on the sample. So F is a vector, okay, and it's in the vertical force, or vertical direction. So the tension testers allow you to determine the strength of a material, the ductility of a material, its toughness, its elastic modulus, and its strain hardening performance as well. So you can get all of that information from one test. And those transfer into different design criteria once you design products, and you determine if you're within the safety zone of making that product. So for example, if you're making a spring or a beam, right, you know what load you're going to put on it. You put it in the finite element analysis. It shows you where the stress points are. And then you determine whether or not those stresses exceed the safety factor. You know, if you've exceeded the elastic limit of the material, for example. So the first thing we're going to learn about is engineering stress, also known as nominal stress. So nominal and engineering stress are the same thing, okay? So we go ahead and we take a look at the basic definition, which is an equation, fairly straightforward. You have sigma here, that's the stress, okay? And then you put a load or a force on your material, that's P. That's a force, right? That's how many newtons is it if you're using SI units. And then below here is a cross-sectional area. And A naught indicates it's the cross-sectional area at the start of the test. So remember, as you're pulling on this bar, this metal bar, it also is getting longer, but it's also getting thinner. So as it's getting thinner, the area is changing. And now later on we'll learn that there's another kind of stress called true stress that takes that into account. But engineering stress does not. It assumes that the cross-sectional area is constant throughout this process. And that's a decent assumption to do to get a lot of information from about your material. Okay, so A naught's the cross-sectional area. So you've got force divided by area. Okay, and those have units associated with it. So you always want to include your units when you're doing your calculations, because it'll tell you if you screw up. Okay, so the question here is, what units is stress given in? Megapascals, that's what the big M is, that stands for mega, and pascals is a unit. Or pounds per square inch, or is it kilograms per meter squared, or is it both A and B? Or is it all of those above? That means, you know, A, B, and C. So I want you to think about it a little bit. You can pause the video at this point, think about it, scratch your head, and pick an answer. And then now we're going to go to the next slide. So pause it if you want to think about it some more, or we'll just move on. Okay, so I don't give you the answer to the previous one. in this slide, but the previous one was pounds per square inch. Okay, let's go back. It's, if it lets me, it's pounds per square inch. That's a pressure, which is what this is. Force over area is a pressure unit. Megapascals is also a pressure unit, and that's in the SI system. So you can use either one. Some people use PSI, some people use megapascals. Now C is not correct. Okay, it's not correct because kilograms per meter squared, kilograms is not a force, it's a mass. Remember F equals ma from your physics class. So it's mass times acceleration. So a kilogram meter per second squared, right? That's a Newton. That's a force. Kilogram meter per second squared. So F equals ma. A is meters per second squared, right? It's an acceleration. And m is kilograms, okay? So kilograms per meter squared is not a pressure unit. Okay, so A and B is the correct answer. Okay, and so that you know that. And think about units. Always think about units. It'll save you many, many times. All right, so we talked about engineering stress, also known as nominal stress. So that's when you pull on something. So remember, our tester, we're pulling on something. We're pulling on something. But we need to measure how much we're stretching it by. That's called strain, engineering strain. Now, engineering strain is an interesting number, okay? It's what you start with, right? L naught. That's what you start with. And then you put a certain stress on your part, and it's going to start to stretch. So let's say I put 70 newtons per square meter on this part, and it starts to stretch, and then it stops at a certain point. That's my final L is there. So my strain is a measure of how much I've elongated it. It's elongation. How much did I stretch it by? So it's the difference between what you end with, because it's going to be longer, minus what you start with, because it starts shorter. Take that difference, and then you divide by what you started with. So it's a percent change is a way to look at it, right? If you multiply by 100%, that'll give you the percent change. So, usually it only gets 0.01, 0.02 bigger, okay? It doesn't stretch a lot. If you keep going, eventually it'll break. And if it's more ductile, it'll stretch more. If it's a rubber, it'll stretch a lot. If it's a metal, it'll only stretch so far and then break. And we'll show you some stress-strain curves that show that. So here's a question, right? So what units is this in? So if we're looking at strain, we're looking at how far we stretched it. But what are the units? And again, look at the equation and try to figure out what the units are. So I'll give you a second to think about it. You can pause the video. Okay, here comes the answer. So it's meters over meters, right? Or millimeters over millimeters, or inches over inches. So it's none of the above. It's a unitless number. It has no units, which is kind of bizarre. But think about it. If I have a thicker, sample, or smaller in diameter sample, I'm going to be able to stretch it at different amounts, right? If you have a thin wire, you can stretch it a little easier and maybe take it a little farther, right, than a thicker one. So this is a way of calibrating or normalizing the data. So it's less sample dependent, right, and more materials dependent. So if you have two different testers, two different ways of making your samples, you should get similar results if it's the same material. Okay? And likewise, A naught, right? When we divide by the starting area for the stress part of it, we can take out the effects of a bigger sample versus a thinner sample. Okay, so it's all about the materials. All right, next slide. So here is a result. So this is a slide that I'd like you to study, and maybe you might want to even print it out. It's in the book. This graphic is in the book. You can see, this kind of shows a timeline, right? You start with a certain length bar with a certain cross-sectional area, A0. Then I'm going to pull on it, and it gets longer. So this is the final length here. Okay, LE. Right? So what they're doing with this dotted line here, they're showing you how the curve looks. So I start with a certain amount of stress on it. I start at 0, but then I increase the stress. I'm pulling, and I pull it harder every time. So I'm going up the stress axis, right? So I'm putting more and more stress on it. I'm increasing the force. The machine actually just applies a force. It's the way the sample is designed that it spreads it out over a certain area. So I'm pulling on it, pulling on it. It gets longer and longer and longer. That's what we're showing here. Okay, so I'm going up this curve. Okay, and that's called the elastic region, where it's kind of straight, and it has an angle to it. It has a slope to it. If I keep pulling, then the material is going to start behaving a little bit differently. Start stressing it out, and it starts to bend over. Okay, so now my force is less, but I'm still making it longer. And that's because it's starting to get thinner and it's easier to pull apart. And then you get to a point where snap, right? It just breaks. Okay, and that's what they're showing this part of the graphic. So this is a really good one to study. Okay, and on the X graph, on the X axis, we're looking at strain, E. So E is this equation again, and it's unitless, and you're showing how much it's straining, right? Basically how much you've lengthened it. So that's L minus L naught over L naught. So L is how long it is at any given point. So in this case, L sub E shows you where the elastic limit is. Okay, and that's gotten this much longer. Okay. And when it starts to bend over, it starts going the plastic region. That's where the material begins to yield. That's why that's called Y. When it starts to bend over, okay, that's called the ultimate tensile strength. And those are important parameters when you're designing. All right, let's move on. So here's your stress strain curve again, and there's some definitions in here. You have an elastic region. That's where it's straight. That's where this this curve is straight. So what happens is if I stress it to this point right here, right, I've elongated it by this much, okay, right here. Okay, now if I let go, the material will snap back to its original length because you're in the elastic zone. It's elastic, it's stretchy. If I go too far and I start to bend over, and let's say I go to this strain or stress, right? And I let go, it's going to follow pretty much this slope back as I release the stress on it, and it won't go back to its original length. It'll be some other length. Okay, because I went past the elastic region. Okay, so this is elastic. Once it starts changing shape permanently, we call that plastic deformation. Okay, this is elastic deformation. Elastic means you can go back. Plastic means it doesn't go back to its original shape. Okay, so study this graph. This is real important. Right here, it starts to go down on this curve because we're not taking into account the smaller cross-sectional area. So the actual stress which is force per unit area, is higher than that because we're not taking it into account. Okay, so think about that a little bit. Here's another example. So again, we're increasing the stress going up, and it's getting longer at the same time. It gets to a certain point right here. It starts to bend over. This is the plastic region. And then we get up to here, and now we decide to unload it. That's what this means. Okay, and it comes back down. And it basically follows this slope here when it recovers. But it's longer than it was when you first started. Now, if you were to load this again, it would go back up this curve and get to this point and then start to continue bending over. Okay, and different materials have different shapes. Okay, oftentimes we use an offset in here to define where this point is. So with very flexible materials, soft materials, you usually will see this this elastic region isn't quite straight. It starts to bend over. Okay, so the question here is, when unloaded, does the cross-sectional area return to the original area? It depends. If you're in the elastic region, let's say you only go this far and you go back, the answer would be, yeah, it returns back to its normal shape. If you go past this elastic point here, where it begins to yield, that's called the yield point, right? The yield stress. Then it starts to go into plastic deformation, and if we let go of it, it won't return to its original cross-sectional area. Okay? So that's exactly what this slide says. It depends how far you went up the stress-strain curve. Okay? If you stayed in the elastic region, you're typically good. It'll return to its original length and cross-sectional area. If you go past the elastic region, then you're in the plastic region. Plastic means it's a permanent deformation. All right, so we learned about the engineering stress, the pressure units. What are they? Think about that. Load over area, what is that? That's a pressure unit. You learned about yield stress. Okay, so you pull on it, pull on it, pull on it, and once it starts to do plastic deformation, then you're in the, you just passed the yield stress point when it goes into plastic. And then engineering strain, that's how much you've elongated it, right? So you're pulling on something and measuring how far you're stretching it. That's what a stress-strain curve is. So the strain itself doesn't have units. Okay, it gives you an idea of how much the material has stretched for a given stress. And then be able to visualize the equation, okay, and think about it as a ratio, you know, of total delta L, the change in length, divided by the starting length. So it's really delta L over L naught, and some people write it that way, okay, where delta L is L final minus L initial.